it just doesn't like me. Okay, so for the sake of the recording, we are going to start chapter 8, section 6, double angle and half angle formulas. Okay. So here is theorem 1. You definitely want to write these down. Like I said, if you don't have a nice little cheat sheet, or if you're making your own cheat sheet, regardless, you want to write these theorems down. You will use these consistently through the homework, I would imagine through the quiz, and definitely on the exam. To example 1. Okay. So this is why I don't like the PowerPoint so much, because it just kind of blurts the answer out at you, and I like you guys to think about it. So we're going to use cosine of 2 theta, and what we're given in this situation is sine theta equals 5/6, and our restriction is from pi/2 to pi. Okay. So because we're given a sine theta, the easiest of our double angles to use would be cosine 2 theta, because it employs, or one of the options is using sine. So let's go ahead and look at how they did it. All right, you literally just plug it in there. Now they didn't show you the intermediary step. They did square 5/6. That's how they got 25/36. But I, of course, assume that you know that. Okay. All right. So that's it. That's how hard that one is. All right. Same kind of deal for example 2. They want us to develop a formula for tangent of 2 theta in terms of tangent theta, and develop a formula for sine 3 theta in terms of sine theta and cosine theta. Now pay attention to example 2, or for part B. You have to do a sine of 5 theta as a 5th degree polynomial in terms of sine theta for your homework. So that example really helps you kind of get in the right mindset of what to do. Okay, so in the sum formula for tangent alpha plus beta, we're going to let alpha equal to beta equal to theta. So when we do that, what do you notice happens on the left-hand side? What do we end up getting? We end up getting what we're looking for, right? Tangent of 2 theta, okay? So that is why they went ahead and made those let statements. Once you simplify everything, you end up getting the 5th equation that could really have been written up in theorem 1. Tangent 2 theta equals 2 times the tangent of theta over 1 minus tangent squared theta. That's another one that you're going to want to write down. And if eventually, like I've said before, your minds are young, so, and they're tangible, so you probably will end up memorizing these. I can tell you that you need to be extremely cautious, more with chapter 7 or with section 8.5 than with 8.6. But if you get frustrated with Pearson, you probably just wrote the formula down wrong. I am speaking from experience. I was very upset last night trying to figure out why I wasn't getting it right. But I persevered. Okay, so for part B, we're going to find a formula for sine 3 theta. And everyone can see that 2 theta plus theta is going to give us 3 theta, correct? Okay, so you're essentially breaking that up, and you're going to use the sum formula that we worked on Monday, except now you're dealing with 2 theta and theta. So now you have to bring in not only the sum formula for sine, but you also now have to work with a double angle formula. So you end up getting, you guys can see the work here, but eventually when you simplify, you're going to end up getting 3 sine theta cosine squared theta minus sine cubed theta. Okay, so that's what it works out to, but you don't have to memorize that one. It's not like, I guess in the future, if someone asks you to find sine 3 theta and you would like to remember that or go, hey, I think I did that, I guess you could do that, but it's not going to be used so often that you would need to memorize it. Okay, theorem 2. I'm going to give you guys some time to write this and resume with recording and go on to example 3. So we want to write an equivalent expression for cosine raised to the 4th power of theta that does not involve any powers of sine or cosine greater than 1. Okay? Excuse me. So what ends up happening here is you end up using the double angle theorem. You end up using equation 7 twice. So you can see that they went ahead and they expanded from the 4th power to cosine squared theta and the whole thing squared. And then they replaced cosine squared theta with the double angle and squared it. And then as you work everything out, you end up with the following. Okay. If you take your time and write it all out, you see it all. It works out. Okay. Assuming there are no questions with that, we can keep the party going with example 4. And again, if you're watching the recording, you can always pause. All right. So we're going to solve a trig equation using identities. So we're looking at sine theta cosine theta equal to -1/4. And our restriction is that it can equal 0, but it only goes close to 2 pi. It does not equal 2 pi. So of course, we're going to work with the left-hand side. If you look at sine theta cosine theta, what does that look like to you? Why should that kind of look familiar to you at this point? So what you can notice is that sine theta cosine theta is nearly the sine of 2 theta, okay? The only thing it's missing is the factor of 2. So we're going to multiply both sides by 2, and then you end up getting sine 2 theta equals -1/2. Okay? So when we think about 2 theta on this interval, you're looking at 11 pi over 6 plus 2 pi k is equal to -1/2 for any k integer. But you have to think about your interval, okay? And obviously we're used to working with theta, not 2 theta. So you have to figure that part out. All right. You plug in your 0, 1, and 2 for k, and then you end up finding that you have theta equal to 11 pi over 12 and theta equal to 23 pi over 12. The last theta is too large. It doesn't fit your restrictions, so you can't use it. But you also need to realize that sine of 7 pi over 6 plus 2 pi k also equals negative 1/2. So you have to do it again. So these problems are definitely long. Please don't get scared of the Pearson homework. I think it starts you out literally back to back with either 2 5-step problems, which are many more steps than 5, or 3. So like they're very daunting looking, but just treat them like little problems and you'll be fine. All right. Example 5 is a projectile motion problem. So far I haven't come across one in Pearson, but that could change. All right, so we want to show that r of theta is equal to 1 over 32 original velocity squared sine 2 theta. Before we go on to look at what that would be, what are your thoughts? How do you think we can get that to happen? Take a look at what they are giving you as r of theta. Notice what they're showing you in that. You have a sine theta, cosine theta. So basically, if you do one small thing, you should be able to get to the goal that they want you at.
So we hypothetically use like the double angle theorem for sine times of 2 theta.
Yeah, so that's exactly what we're going to end up doing. So if we plug in the double angle theorem, what you have to do is you have to do it in a way that you can't just shove a 2 in there and say, oh, I'm going to replace this. You have to kind of use 2 over 2. So the 2 helps you on top to get the replacement, and then you take the 2 on the bottom. 2 times 16 will give you your 32. Okay, so it's a really easy fix there. You're just going to multiply by basically a special factor of 1, which is 2 over 2. All right, so before we go on to part B, let's think about it again without looking at the answer. Find the angle theta for which r is a maximum. So before you go blurting anything out, anyone, think about your sine. Sine has a general curve, right? It has a maximum of something. So use that idea, figure out where that maximum happens, and then remember that you're dealing with a double angle, so you have to cut that in half, right? So where do you think it's going to be? What do you think? What do you think you could end up being? What angle?
Like 45 degrees.
Yeah, exactly. Great job. So here's the discussion that goes with it. If you guys need to look at it, but we basically had the same discussion out loud already. And then I'll give you a second to look at how they worded it. Okay, and then here just kind of verifies that 45 degree. So zoom 5, you got it. Great job. All right, so we're actually already on to objective 3, which is using half-angle formulas to find exact values. You use the half angles like crazy in the Pearson homework, right? Definitely get familiar with these. I will tell you the one that I kept forgetting and the one that was making me mad. When you do the double angle, in fact, I'll just show you guys it. So apologies, but we will come back, no worries. All the way back at the beginning. Do you guys see how there's a 2 in front of the sine squared theta and a 2 in front of the cosine squared theta? That little 2, not the squared, but the 2 in the front, because you're writing a double angle, for some reason with my brain, I was okay with the first one with sine and the 2 sine cosine theta. My brain would drop off the other 2's. So definitely remember them and pay attention when you're writing it, because Pearson was just yelling at me constantly and I kept getting it wrong and getting frustrated. So definitely remember all the little formulas. All right. So half-angle theorems. Here it is, 9. I don't know why they don't separate it out. Honestly, if I were you guys, I would call it 9, 10, and 11. They're just calling it 9. There is a 10, 11, and 12 and a 13 in this, but I don't see why they're not separating these out. It's not one large equation, it's 3 separate ones. So I guess however you guys want to label it is up to you. I left it the same, but I could understand why you would want to expand them. All right, and if I ever go too fast, you can always use the video to rewatch it. All right, theorem 4, half-angle formulas. Here's where you find the true 10, 11, and 12. I'm not going to read them out to you. You can obviously see them and you know what they are. What I will point out here is that where there's a plus or minus sign, this is determined by the quadrant of the angle alpha divided by 2. So it doesn't necessarily matter where alpha is stationed. It matters where the half is. So, you know, if you're looking at, I don't know, 110, 110 potentially could fall differently than 55, okay? All right. Okay, so the next example, it uses the half-angle formula to find the exact value of cosine of 75 degrees and sine of negative 75 degrees. They're very similar in what we have to do. What you first have to realize is that because 75 degrees, you're not going to want to cut 75 degrees in half. So you kind of have to work a little bit backwards to go forwards. You're actually going to realize that your alpha is 150 degrees. So then when you worry about your sines, you are going to look at 75 degrees. Okay. And here they explain that because 75 degrees is in quadrant 1, the cosine of 75 degrees is going to be greater than 0. So we're going to choose the positive sign using the formula. And then literally you guys just plug it in and you simplify. There are calculators out there, radical calculators. So if you really have a hard time, if you keep getting things wrong on Pearson, like over and over and over again, and your issue is just the simplifying the radicals, you can use one of those. I won't stop you. Do not, huge caveat, do not give decimal answers. Do not put a decimal answer into Pearson. They want the exact answer. They want the one with the radicals. They do not want decimals. Okay? So please don't email me scanning me your work and saying that you want credit, because even if it's equivalent, this kind of work you have to show the exact the exactness. So Pearson won't take it if you put in the decimals. All right. So here we're going to use the fact that sine of negative 75 degrees is also equal to negative sine of 75 degrees. And it, like I said, very similar to the first one. You just pull the negative out. And that's that. Any questions to that point? All right, to everything we've worked on to this point. Okay. We are almost done. All right, example 7. If the cosine alpha is equal to negative 2 over 3 and our restriction is from pi to 3 pi over 2, they want us to find the exact values. Okay, so exact values, again, meaning no decimals. You're going to have radicals in your answer. Get used to them. Don't hate them. Don't think it's gross and that you messed up. It's just the way it is. Okay, so the first thing we have to look at is we have to find where alpha divided by 2 would sit. So we're looking at between pi over 2 and 3 pi over 4. So that means we're looking at quadrant 2. Okay, so that does tell us some things about our sines and cosines. All right, because we're looking at quadrant 2, we're going to use a positive sign for sine. And when you simplify and plug in and work everything out, you end up getting 5 square root of 6 over 6. All right. Make sure you guys are taking the time to write everything out. Even if you can't write it out with as fast as I talk live, make sure you watch the video and pause it if you need to. Okay. You can also follow through on the PowerPoints yourselves in Canvas. Right. All right, so part B is pretty similar, except we do know that we're going to use the negative sign for cosine because it is in the second quadrant. When you plug everything in, you do end up simplifying down to negative square root of 6 over 6. I would take the answer as not rationalizing. Pearson probably never will. So if you end up forgetting to rationalize on the exam or on the review or whatever, I will still take it. I'll probably just write something like don't forget to rationalize in the future. I highly recommend you guys print something out like this. It's a special angles chart. If you don't want to print it out, then you can obviously hand copy one. Comes in pretty handy. Makes it so that when you're doing your homework or the quiz or whatever, you're just worrying about the concepts and not memorizing everything. If you haven't figured out by now, I'm not the kind of professor that cares if you can memorize. I really just care that you can work the concepts. Okay. All right, so the last one, tangent. Tangent is also going to use the negative sign in quadrant 2. And when you plug everything in, which if you notice, if you look here, do you see how you have 5/3 on top here? And then you have 3/2 on the bottom here. Well, there was a reason why I said that. I don't know. Some of the times I don't know if it's alpha divided by 2 or if it's dealing with the double angles. You can use the trick that we're used to using with sine and cosine for tangent, and sometimes you can't. So you just kind of have to go with it. Sometimes you end up seeing it and it works, and sometimes it doesn't. So if I were you guys, I would definitely just use the formulas. I would not go based on the way we used to do things. It just doesn't always work all the time. And I can't really answer it for you, except that I'm right there with you and I look at things differently. And the Pearson just is like, no, you're not allowed. Okay, I'll do it your way. All right. Half angle formula for tangent is written in 2 different ways. You can have it either written with an expression for cosine on top, or you can have it with the cosine on the bottom. Just kind of pay attention to the different signs. Okay, I am going to stop the recording.